using our DDR sysconfig tool for AM62 and the new Samsung DDR that was identified for BeaglePlay. Why we are doing this session is for us to take this as a training for the rest of the teams to get the settings right. And you could probably walk us through the stuff, the gotchas, and potentially what we need to be careful about.
Right.
What am I looking for? And what's the information that I'm lacking? You could probably start from the having a comprehensive data sheet is the first step towards getting the configuration right. So what do we need to look for? Next stage is how do I translate the parameters that I see in the data sheet? For example, the speed settings might be not exactly what our chip supports, right? That was one parameter you were kind of indicating to me when we were talking. If you can walk us through that, end of the session, I'm hoping that we have a nice little DTSI and header file that will magically work. But the boards are not in yet. They'll probably appear in a couple of weeks. We'll verify it at that point.
Okay. All right. So this will be a little rough, but I think I can walk you through it here. So let me share. Okay, let's start with where we go. Dev.ti.com sysconfig. Let me get rid of this. Okay, I think there are direct links to this thing, but it's from the main sysconfig page. You're going to want to choose this software product, DDR config tool, and then you're going to want to choose the device that you are using and hit start, and you'll come to this kind of a page, which is so all of this stuff in the middle here is what we're going to want to configure, and then the output is over here on the right side. So in your case, you want to add a LPDDR4 type of memory. Okay. So what this will pre-populate all of these parameters. This pre-populates the parameters that are used on our EVM, on our, let's see, in this case, it's the, I guess it would be the Q, AM62x Q100 package. So if you notice here, all of these parameters are pre-populated, and those are the ones that are used on the EVM. So when you use a board with a new device, and I'm going to go to Nishant's email that has the device data sheet. And give it a second to pop up here. Okay. So here's our data sheet. So let me shrink this down a little bit here. So the tool is intended to, obviously facilitate programming the literally hundreds, maybe thousands of registers in the controller and the PHY, the DDR controller and PHY. So let's start with at the top. This is a 16 gigabit. Oh, this is a DDR4, not an LPD. I thought this was an LP4. I'm sorry. That's simple enough to change back. Okay, so this will, again, the default will be what's on the AM62x board, EVM board, SK board. So our maximum frequency on 6.2 is 800. You can go lower, but you can't go higher. So we'll start with 800. So this is all the system configuration, kind of a high level type parameters. Okay, our bus width is going to be 16 bits. You're not going to be able to, well, okay, you could change to 8, but for the most part, you're going to be at 16 bits. We're at a 16 gigabit device, as shown here. And you only have the choice of, you only have the choice of one rank. and just nominal operating temperature. And we encourage and recommend that you keep the DBI enabled. And this is just a feature of the memory that we found is better enabled. We found this on AM64 SK. It just reduces a lot of noise on the board. So our global recommendation is to enable this feature. So this should stay enabled. So these next categories here are latency parameters. So to be honest, a lot of these parameters, the latency parameters, the timing parameters, are all JDEC compliant, typically for a device. So for the most part, these will remain, a lot of these will remain the same. And as you can tell, there's a ton of different parameters here. So let's start with the latency parameters. In the DDR4 datasheet specifically, there's something called the speed bin table. Hopefully they're in here. And these are parameters associated with the operating frequency of the memory itself. So even though we're working with a device that may have a speed grade that's faster, and in fact, I think what Nishant sent me, let's go back to that email. Yeah, you didn't send me a specific part number, but as you can see, let's see, maybe.
We have the schematics. I think we can pull that up. Hold on.
Okay, well, regardless of what the part number is, actually it looks like, yeah, so here, for example, here are some of the part numbers associated with this particular device. And as you can see, this part number can run at a maximum data rate of 2666, 2933, 3200. So these are the maximum speed rated speed grades of these devices. So whichever one you happen to be using, you would go to that particular speed bin table. So let's just, for example, I'm guessing you're probably running with a speed grade of this one, this 3200. So let's go to that speed bin table. And you scroll through these things here. And here's the speed bin table for DDR4 3200 right here. Okay. So, however, we're not running at 3200 mega transfers per second. Our maximum for AM62 is 1600. Okay, or 1600 MTS or 800 megahertz. Our maximum on AM62 and AM64, for that matter, is 800 megahertz. Okay, that corresponds to a clock period of 1.25 nanoseconds. Okay, so in this speed bin table, this row here, these three rows actually, is what you would be using for the device that operates at 800 megahertz or 1600 MTS. So this is where you end up getting your cast latencies, CL, and your cast write latency, CWL. And so that's what ends up going into this portion of the spreadsheet. Now, in this particular case, I happen to choose a CL of 14 and a cast write latency of 9. I think you have actually several different choices here. And notice I'm picking 14 because I want to use a CL that's associated with read DBI enabled. So you would have the choice of these three basically, 12, 13, or 14. And actually, if you come over here, you can see that actually 12 is for some reason reserved. So that wouldn't be a choice. So you're really choosing between 13 and 14. And then you're also choosing between a CWL of 9 and 11. So it just so happens on the EVM, I'm running with 14 and a CWL of 9. So that's why I chose those two. Okay, so those are those two parameters. So those may change based on your operating frequency. So if you happen to run slower, then you would move up here. Wait a minute. Yeah, it looks like you can't even run slower with this particular device. So this is actually the slowest you can run, somewhere between 1.25 and 1.5 nanosecond cycle time. Okay, but anyway, these parameters would change with frequency. So if you happen to move to for example, a 62A device, these cast latency, cast write latency will increase depending on the increase in speed. So that's when those two would change. Okay, so now let's go to the second block here. These are just all timing parameters. And in general, like I said, since we're working with a similar device, similar timing device, speed grade device, a lot of these will be the same. But if you want to double check them, then by all means, all you got to do is search for TXPR. And here it is right here in the data sheet. And since we're working with a 3200, let me move over here. Since we're working with a 3200 speed grade device, then we would use this particular parameter. So this is saying you want to take the maximum of 5 clock cycles or TRFC minimum plus 10 nanoseconds. Okay, so that's a little confusing. But the point here is you just take those, you would just plug those two values into the tool, and the tool will do the math for you to determine which one of these ends up being the maximum timing parameter. So in our case, our TXPR TCK is either 5 clock cycles or okay, there's either 5 clock cycles or it's TRFC plus 10, which is actually automatically calculated once you plug in TRFC as well. Let me take another parameter that has both. And I'm in the process of cleaning this up. So for example, let me find one that has 2. Okay, here we go, like this TFAW. Okay, so this has a clock-based minimum and a nanosecond, an absolute parameter minimum. So let's go to that particular parameter. Okay, so now you can see that, oh no, there's 3 different parameter parameters actually for TFAW. So what does this half K, 1K, 2K mean? Well, this means that the parameter changes based on your page size for the DDR. You can do half a kilobyte page size, 1 kilobyte page size, or 2 kilobyte page size. Well, what kind of page size do we have? Well, that you would find typically at the top. And so let's see here. Yeah, so this is where you would determine which type of device that you have. So depending on size, you could have 100 megabit, 128 megabit, 256 megabit, blah, blah, blah. And you can see the page size here. The page size would, in this case, would be 2K bytes, 2K bytes.
I think it is the
2K bytes.
It's the 16 version. 16 GB.
It's this one, yes. Okay. So I'm just saying that there's different tables. Okay. So in our case, we're using the 16 gigabit device. So our page size is 2 kilobytes. Sometimes this will change if you have, for example, a 2x8 devices as opposed to 1x16 device or something like that. Okay, so now we know our page size. So let's go back to where we were. So now we know we need to use TFAW 2K with the 2K page size, and we use, and so our parameters are 28 clock cycles or 30 nanoseconds. And so in the table here, I would just plug in 28 clock cycles and 30 nanoseconds. And as you can see, I didn't have to change anything because this is the same as what was on the EVM. So you would do that for every one of these parameters. And for the most part, like I said, I would say 90% of them would stay the same. There's only a handful of parameters that would change based on maybe device size, device density, or maybe the speed that you're operating the device, or the, I'm sorry, the speed grade of the device, for example, okay? Okay, so there's a lot of parameters there that you would go through, and basically, so for every one of these, you would search for it in the data sheet and then plug it into the tool. Again, this is all JDEC spec type of data, so you could actually, you know, for the particular device that you're operating, you can actually get a lot of these values out of the JDEC spec itself. All right, any questions? Let me stop and any questions so far with these two groups that we've talked about. So this is all DRAM timing parameters is what we've just input into the table. Okay. Clear as mud, right? Okay, so I'm obviously not going to go through all of them.
So is there a difference timing A, timing B, IO control A, IO control B?
Yeah, so this is both of these are DRAM timing groups. So it's just the way we grouped them in this particular tool. There's no real reason, I guess. I'm sort of in the process of you know, alphabetizing these guys here. So I did this on 62A. I alphabetized them, so it's a lot easier to kind of search through and, you know, and then kind of step through them and then go through the table. But so this needs to be cleaned up a little bit. But there's no real reason why we divvied it up this way. It's just a little bit easier to modularize, I guess. Okay, so those are the timing parameters. So now we talk about the IO controls. So on there's IO control on the processor side on AM62x that you have to configure, and then there's also IO control in the memory that you have to configure. So on both ends, you've got to configure the IOs. Now on DDR4, it's a little bit simpler. If you go to the LPDDR4 table, there's a lot more entries in there. But since we got a DDR4 here, let's focus on DDR4. So, so a lot of time for most of the time for a board, you would run board simulations, signal integrity simulations to determine if your board design is appropriate and won't fail once it's fabricated. And out of that, typically, you would get driver impedance values and ODT values. So this is driver impedance for when AM62X writes out to the memory. It's the drive strength setting essentially. And we can set that for both data and address. And then on the memory side, there's a termination resistance. And so that's what we call on-die termination. And so that's set for data on the memory side. And so for, I'm sorry, I take that back. We're driving data out on a write, so we are concerned about driving our address and driving our data from AM62. And then on the memory side, the termination is set down here in the memory. So in this example here, we have a 40 ohm drive impedance for both data and address, and 40 ohm termination in the memory for this particular, for a write transaction, essentially. So again, all these values would typically come from a simulation, some sort of signal integrity simulation.
So James,
that's done on the board.
How do we get the on-die termination resistance value? Isn't that supposed to be part of the data sheet kind of thing?
No, this is part of, again, this is part of board simulations. So, you know, in this case, our drive impedance and termination are equal. So, you know, this is all, and I could get into, you know, what the I/O structures look like for DDR4. They're actually different for LPDDR4. So this is just the way the I/Os are configured for specifically for DDR4. And this comes out of, this is not in, I mean, the data sheet does have information about how the termination is implemented, but the actual choice of the value comes from your board simulations. That's a whole other training session on how to do these board simulations, you know, for different designs.
But is there something like, are the defaults safe-ish enough?
So that's a good question. I mean, you could, the values here for the EVM, if the design is similar to the EVM, I would say that these values are probably what you should start with. If you don't have the luxury of having simulation results, you can certainly start with these values. They may not be optimal at your maximum frequencies or at low temp, high temp. You know, once you start getting into PVT type testing, they may not be optimal. But to get a functional, a board functional, these may be adequate.
Okay, got it.
Okay, so I think the fact that we're running at relatively low speed, 800 megahertz, I mean, that's not low, but it's definitely, you know, lower than the speed grade of this device for sure. And then if you've got a pretty robust design, then you could probably, then these values are not as critical as it would be on an AM62A design running at, you know, a 3200 MTS or whatever. So I think you've got a lot of margin at the speeds that we're running AM62X. And so these values may not be as critical. That's where you start getting into, you know, your board, your eye diagrams, and determining what kind of margin you have on your boards. Now we're working on maybe some tools associated with that are a little bit more. So similarly, for a read, you know, for a read, the memory is driving the data. So that's where driver impedance comes into play here. And then on our side, on the AM62X side, that's where the termination, the on-die termination comes into play. So these two, and basically these three are associated with the driver settings and termination settings for the IOs. on the device. Now, you also have the ability to change VREF control. I would not, I mean, these are typically, I would leave them the way they are. This eventually, like for an LPDDR4, they eventually get trained. But these are set for DDR4 VREF levels, essentially. So this is probably something you would never really adjust in your design or in this configuration. Okay. So everything else here pretty much stays the same. Or if you don't have any simulation results, I wouldn't mess with either of these groups, IO control A or IO control B. I would just stick with what the EVM has and see if you can get functional until you can get the tools to figure out how to measure eye width and height. Okay. So, and that's it. So that's